At the end of the last slide set, we were talking about the thermal characteristics of water, and I kind of sped through things, so I want to kind of highlight this again because it's very important as we go through the rest of the semester in this class. These characteristics will come up again. So just recall the thermal characteristics of water are very important. And also know that these numbers are actually quite high compared to other substances. So water is especially efficient at storing energy and then releasing energy. Now, how does that work for us in oceanography? Well, when water turns into vapor, it then goes up into the atmosphere and can be circulated around, which helps store and transfer energy. It's also going to happen if you just warm up the water and start circulating it. It can start to move the energy around the surface of the earth. And when ice forms, it absorbs or it gives off heat. And when it melts, it absorbs a significant amount of heat. So even the formation and melting of ice is going to be significant. When you look up in the sky at a cloud, clouds are made of water droplets, so vapor is turning into liquid and releasing energy. But clouds are also made of little ice crystals. And when we go from gas to solid, which is the ice crystals, in order to do that, we have to release 540 calories per gram plus 100 calories per gram plus another 80. So that's a total of 720 calories per gram released when you turn water vapor into little ice crystals. Again, that is a significant amount of energy being released when clouds form. So this energy is really what powers the weather. When water evaporates or turns into vapor and goes up into the atmosphere, we can't see it. Water vapor is invisible. But when that happens, it has absorbed a significant amount of energy. When it comes out of vapor form and turns into liquid and ice, we see a cloud. And again, that is releasing a significant amount of energy. This actually helps moderate the temperature of the Earth because the sun's energy hitting the Earth's surface is then absorbed by water, which turns into vapor. Or if you're near a large body of water like a lake or an ocean, that's also going to absorb that energy and prevent a very large change in temperature. Alternately, you could be in a desert area, very, very dry, not much water available. And if you're in a desert area, when the sun comes up in the morning, the temperature starts to go up. So if you ever look at the temperature swings from day to night in a desert area or a dry climate, you'll see that the temperature changes significantly more than it will if you're in an area that has a significant amount of moisture, and it changes even less if you are near a large body of water like a lake. So Lake Michigan moderates the temperature of Chicago, or an ocean. The Atlantic Ocean moderates the temperature of New York City, and the Pacific Ocean moderates the temperature of Los Angeles and San Francisco. So this is kind of the official technical slide, so it gives you some more information there. One of the things to notice down at the bottom is that freezing and thawing of ice also moderates the Earth's temperature. So there's a really big role that water is playing. And this slide shows the temperature of the world's oceans. And what you'll notice is there's some slight variations here. Off the east coast of the United States, you'll see there's some warm water headed up to the north. And over here by Europe, it helps warm Europe up. And if you look at the west coast of the United States, you can see cool water coming down along our west coast. And that will help keep the west coast a little bit cooler than you would otherwise expect. That's what makes California such a nice place to live, is the presence of that water. So we want to shift now and talk about a few of the other important properties of water. One of them is density. And we will talk about density quite a bit when we talk about ocean circulation. It's an effect of temperature, or it's affected by temperature, I could say. Colder water is generally more dense. If you look at this graph up here, you can see that line of increasing density as the temperature goes down. You'll notice that there is a little bit of switch here, a little lowering of density as water gets beyond 4 degrees centigrade, which is 39 degrees Fahrenheit. The density actually starts to go back down, and the density drops big time when it freezes. And the act of freezing, the water molecules arrange themselves in this crystalline structure you can see. One of the things you can't really tell from these drawings in your book, but is very important, is that when the water molecules organize themselves into a crystal, they actually spread apart a little bit in order to set up that crystalline structure. That means that ice is less dense than liquid water. This is very, very unusual for solids. In most cases, when the molecules organize themselves into a solid crystalline structure, that structure is more dense than the liquid version of that substance. And so solids typically sink in a liquid of the same substance. So water is a notable exception of that, and that means that water is going to float. One of the important aspects of this is that because ice floats, it is susceptible to receiving energy from the sun. So the sun can then melt the ice that's floating on the surface of the ocean. If water were like other substances and ice were more dense than the liquid water, most of the ocean would end up being frozen because water would freeze at the surface, it would sink down to the bottom, and a layer of ice would build up at the bottom, and you'd have a kind of a thin layer of water at the surface that would be seasonal, but the deep part of the ocean would be mostly frozen. So the fact that ice is unusual and less dense than liquid water also means that our oceans are going to be oceans of liquid water instead of solid water or ice. So some comparisons of seawater versus pure water, because we've just been talking about water in general, but seawater is not pure water. Seawater contains, as we'll find in the next chapter, about 3.5% dissolved solids. And the presence of dissolved material in seawater is going to change some of these characteristics. The freezing point will be a little bit lower. It's going to be a little bit more difficult to evaporate seawater compared to pure water. Salty water also has a higher density than pure water. So these characteristics are, again, a little bit different than pure water. It's important to note that the ocean is stratified or layered due to density. This diagram from your book shows that the deep water, the deep zone, is dense because the water down there is cold. Remember, it can't get energy from the sun. And also cold water is more dense, and so it sinks. And it's also salty. So, and we'll talk, when we talk about ocean circulation in a few chapters, we'll talk about how that happens. But the deep zone is cold and salty and therefore more dense, and that's why it's down there. The surface water is less dense because it's warmer, and depending on where you are, it may be less salty as well. So that leads to our density stratification or layering due to density. And we're going to wrap up this chapter by talking about the behavior of light and sound in seawater. And so an important aspect to understand is that waves, and light behaves as if it were made out of waves. It's a little more complicated than that. If you take a physics class, our light behaves as if it were made of particles, which we call photons, but also as if it were made of waves. So light will bend or refract when it goes from one substance to the next. And sound will do the same thing. So variations in the water will cause the light to bend just as it shows in this picture here. So light will bend and sound will bend. So keep that in mind. But let's talk about what light actually does when we're in the ocean. Three things happen to light when it enters the ocean. Number one, it refracts, it bends. Light travels more slowly in water than it does in the air, and so it will bend when it goes into the water. The light will also be scattered by the molecules in the water. And it will also be absorbed. And this last point is really important. The absorption is what allows the water to take in energy from the light. And then that energy causes the molecules to move faster, which raises the temperature. So energy from the sun is absorbed by the water, and that raises the temperature of the water. And so that's an important component that we'll be discussing when we talk about weather, as well as ocean currents. These characteristics will vary with the wavelength of light, and the wavelength of light is what we experience as different colors of light. So how does that look? How does that play out? Well, in the ocean, at the surface, we have what's called the photic zone and the aphotic zone. The photic zone is where there's enough light to see, and the photic zone is also divided into the euphotic zone, where there is actually enough light for photosynthesis, and the dysphotic zone. There's enough light to see, but not enough light for photosynthesis. And then once you get down below about 600 meters, the ocean is just completely dark. And the depth of these zones actually varies with the characteristics of the ocean water. So if there's more sediment, if the angle of sun is lower, the light will not go as deep. So you can see that in these two diagrams here, that in different places in the ocean, the light can go deeper, and in some places, the light will be much more shallow. And again, it's going to depend on what's in the water in terms of sediment and dissolved materials, and also the angle at which the sun is approaching. So that's light. Our last characteristic is going to be what sound does in the ocean. And it turns out that sound is the opposite of light. So light goes more slowly through water. Sound actually goes faster. Sound travels when one molecule is able to vibrate its neighbor. So in the atmosphere, the molecules are far apart, so it's difficult for one molecule to vibrate its neighbor. In the water, because water is more dense, sound is going to travel farther and faster in the water. It's much more efficient. The only reason you can't hear well in the water is because your ears are geared toward receiving vibrations in the air and not in the water. Organisms that live in the water, as we'll find at the end of the semester when we talk about life in the ocean, those organisms have different techniques for hearing things that are going on in the ocean. So the key factors for sound traveling are temperature and density. The warmer the water is, the faster the sound will travel. And the denser the water is, the faster the sound will travel. That leads to this kind of interesting profile that you see on the right, which is at the top of the ocean, because the water is warm, the sound travels fast. At the bottom of the ocean, the water's cold, but it's also much more dense, and so again, the water travels quickly. This leads to a very interesting characteristic at that minimum velocity layer at about 3,000 feet or 1,000 meters. These sound waves will bend back in. As they try to leave, they bend back into the lower velocity layer. And so this creates what oceanographers refer to as the SOFAR layer. And sound will travel an extra long distance and stay focused if it is emitted in this layer. So you can see it bending back in. And that will conclude the slides.